Okay. Any question about the previous session? Today we want to continue our discussion about GANs, and especially we will talk about f-GANs or functional GANs that are an extension to the original formulation of GAN. Do you see any marker? No marker. So let's recap what we have seen previously. We see that the general loss function or distance metric based on likelihood may not be a great option due to the discrepancy between the concept of great samples and great likelihood. It seems that they are not generally in one direction. It means that when you have a great likelihood, you do not have great samples necessarily. So we are thinking about something different from likelihood, and the new divergence metric that is going to be designed is such that we calculate the divergence just based on samples from the distributions we are dealing with. It means that the data distribution and the model distribution. Just by having samples from these two distributions, we want to calculate the divergence. Okay, so because we just need the samples, we see that one approach to design your model is a model that accepts some latent samples from a latent distribution and pass them through a generator network and generate the samples. This is enough as the generator model, as the generative model. Why? Because you just need samples and you do not need the direct access to the distribution. So it's a great option to be used as your generative model. And the next point is that to design the divergence or distance metric, we design a labeled data set. That labeled data set is such that each sample is labeled by its origin, whether it is coming from the data distributions or it is coming from the model distributions, it is labeled. So you generate this labeled data set, and then we see that a potential distance metric can be a classifier that works on your labeled data set and based on the input decide whether the source of the generation is your true data distribution or it is coming from the model distributions. When it is coming from the model distribution, an optimal discriminator will assign 0 at the output, and on the other hand, it assigns 1. So then we talked about how we can translate this divergence and this classification error as the divergence, and we see that the classification error has its minimum when the two distributions are matched. Although it is a classification loss, it can be indicator of the distance between distributions generating data, and it is 0 when there is any discrepancy between two distributions. So it can be considered as a great option. Then we characterize the family, and the distance metric, and then we come to this justification that I want to talk about more today because there is some problems with my presentations at foundation part. The justification said that this is the justification for the name generative adversarial nets, or this optimality condition. we see that if whatever you select as your generative model, the optimal discriminator is the discriminator that is the ratio of these two functions. It means that the ratio between your true data distribution and the summation of your true data distribution and your model distribution. And we see that by working on the loss function of GAN, we reach this point. Yeah, we reach this point. Okay. In the foundation presentation, I made a mistake about the Jensen-Shannon divergence. The Jensen-Shannon divergence definition is exactly what you have seen here, except for a factor of 1/2. The JSD, I updated the presentation for you in the Canvas, but just to have that justification here too. For the JSD between two distribution P and Q, it is defined as half of the KL divergence between, this was the problem, this was my mistake before, between the first distribution and another distribution that we name it M, plus the KL between the second distribution and again this M distribution. And what is the M? M is Q plus P/2. It means that for any input X, to calculate the probability using M, you first calculate the probability using your P function, your P distributions, and then your Q distributions, and then divide it by 2. It is clear that it obeys the axioms of PDF, so it is a valid PDF, and you can calculate the distance between P and M, Q and M. The most important point is that when assume that this is P, for example, starting from 1 to 3, this is your PDF, P as a function of X. And this is Q starting from 0 to 2. For these two functions, both of these two KL divergences both of them are infinity. Why? Because there is some places where one of them is 0 and the other one is non-zero. These two places. And we know that based on the definition of the KL divergence between P and, for example, Q is the expectation. Let's write it as the integral. If there is a place where P is non-zero, for example here, but Q is 0, we have infinity problem here. And on the other hand, for the KL between Q and P, we have the same problem. But pay attention to this M. What happened with this M? This M sum these two PDFs together, and as a result, the range of X where M is non-zero is starting from 0 to 3, something. So what happened? When you have this formulation, it means that for the places, you do not have any problem of infinity here. Why? Because it is non-zero in all the range of both of them, in the union of the range of the first distribution P and the second distribution Q. It is non-zero, so you do not have the problem of infinity divergence. So this was the problem, the mistake in the definition of the Jensen-Shannon divergence. I updated and considered a new presentation. And you can see clearly the Jensen-Shannon definition here but the twice the Jensen-Shannon divergence. So this is the 2 times Jensen-Shannon divergence between p theta and p theta minus the log of 4. So potentially the GAN seems to be a better distance. Why? Because when you are working with KL, you may have problem of infinity, because KL is just based on sampling from one of the distributions. So when you are sampling, it means that you are sampling from p data in your KL divergence, and if the data, if the sample is coming from the place that your model assigns 0 to that data, for example, one of the training data is such that in one iteration of your training, p theta of xi is equal to 0. So you have this is very rare situation, but it can happen. So it seems that GAN is a better because it uses JST, and JST does not have the problem of infinity value. Any question? Yes.
So for the distribution that you drew, if it's possible to like totally separate them so that they do not have any overlapping, right? In that case,
even if they do not have any overlapping, again the JST is not it does not have problem. Why? Because assume that P is here and Q is here. Okay, then their average again cover both of them. Okay, and in KL, in each of the KLs, you are sampling from either Q or P. Why? Because you are not sampling from M. You are sampling from either Q or P, and both of them, when you sample, the M is non-zero.
Yeah, like you never ever sample from that.
Yeah, exactly. You never ever sample from some places that lead to to infinite problem. Any question? Okay. So please pay attention to the updated version of your foundation slide. And now we want to continue our discussion about GAN. We know that this C theta is not achievable. Why? Because in this derivation, we assume that you can consider the optimal discriminator, which is not realistic in what you have in practice. Okay, just a justification why this divergence or this distance can't be a good option for training. Okay, but if you have if you have a large enough capacity in your discriminator and you have a great optimizer, then you can consider approaching this C theta in your training. Okay, so again, here show that the minimum of this C theta, the best model is the model that results in C theta equal to log of 4 minus log of 4, and thus P theta equal to P data is the global minimizer of C theta. We see the training algorithm. This was a simple example, and these were real world data sets. And this was the DC GAN, which was a effective demonstration of GANs when immediately after the GAN was proposed. And we see that the architecture is based on convolutional neural networks, and only with one pass of the data set you have achieved reasonable generation performance. And this was the concept of attribute vector in GAN, equivalent to VAEs and the attributes vectors. So now we want to talk about a major problem in GANs, in original GANs, which is the mode collapse, and it is an important point to understand. Assume that we are in a training procedure, and now we have this result. What is this result? The blue boxes are generated samples, and the red ones are the data samples. Okay, so now you want to update. You see that the discriminator is perfect. Is it? Do you agree? The discriminator is perfect here. Why? Because it can ideally discriminate generated samples from the data samples. The red parts are the parts that the discriminator outputs 1, and the white part is the part that the discriminator outputs 0. So it is the optimal one. What happened when you update the generator now? The generator changes the position of this blue line because you do not change the discriminator, okay? So the red regions are fixed. You just want to update the generator. The discriminator is fixed. So these two regions are fixed. What happened to the blue, to these blue boxes? To this blue, what?
Move towards red.
Move
towards the red region.
Yeah. Why? Because the generator wants to resemble the data distribution. It wants its samples to be near to the places where the data probability is high. This place, or this place. Okay? So when you update the generator, this happened. It means that all these boxes approaches the nearest concentration place of your data samples. So some of them also enter the regions that the discriminator decided data samples. Okay. So in this figure, the performance of the discriminator is not optimal anymore. Why? Because the discriminator assumes that these samples are coming from the true data distributions while they are generated. Okay? Clear? What happened next? Now we want to update the discriminator because it is a sequential optimization. What happened if I update the discriminator here?
Radius 3.
What?
The radius 3. The radius of circles.
Yeah. It reduced the dimension of the circle so that only the data samples will be inside its decision boundary as one. So again, it's optimal. Why? Because all of them are outside, and the only samples inside the region which is indicated by 1 are the data samples. So what happened next? I want to update the generator. Again, they approach. Again, the generator samples approach the data samples. This is exactly what the loss function is imposing. It imposes this generative model samples to be as near as possible to data samples, so that the discriminator misclassified them. So I have this situation. Now assume that the capability of your discriminator is not as much as the reducing the dimension of this circle anymore. Maybe it can. No, it cannot. What happened? What do you think? The discriminator, because the discriminator assumed that these are the data samples and these are the generator. Oh, we have major problem with this marker. Yeah.
Wait, so can we just in the beginning find average of those red points, right? And then the red point that's furthest from that average will be the radius of that red circle. Can we do that instead? So that's just one iteration, but here we have multiple iterations.
Yeah, the point is that this is just a simple demonstration of what happened in practice. In practice, you do not have these types of region boundaries, and it is much more complex than that. And you have a limited capacity for your discriminator. The discriminator should be capable of extracting this part, and also it should focus on this part. Okay, when your generated samples concentrate around one peak of the data samples, okay, what happened? Finally, the generator cannot make much more complex region boundaries. Because if they continue this procedure, at the end, the boxes will be here. And the discriminator should have something like this. Boundaries, okay? Boundaries around each data point. This is the extreme case. This is not what happened in practice, but conceptually, this is the problem. And having such decision boundaries needs lots of capacity in the discriminator. Because discriminator not only wants to discriminate other parts perfectly, it also wants to concentrate, to focus on the place that the generated samples, let's say, attack your data samples and wants to be confused with them. Okay? And conceptually, it needs a very large capacity to model these regions. So this is not the case. What happened? At some point like this, the discriminator decide to tolerate misclassification of the red parts, and then put all of them as generated. This is better classification. This is better classification than this one.
Yes, say that again.
Yeah. You know, the discriminator understands that the generated samples are attacking one colony or one peak of the data sample. And they are approaching that peak. This is a peak in data distribution, okay? So, in the starting iterations, and when they are not very near to the peak of the data, like for example this place, what happened, for example here? The discriminator capacity allows to reduce the dimension of this region so that you have these regions, classification regions. But as they approach the peak here, further and further, you reach the situation that the discriminator must have something like this. Discriminate each point even. This is the extreme. This is not what happened in practice. But something like this needs a high capacity in the discriminator, you know? So finally it decided that to completely consider all of these data as generated, even you have some misclassification here, while you do not have any misclassification in other parts. Because if you want to put more capacity here, you should reduce your capacity here. So this is the optimal point when they attack the data samples. So at this point you have this type of samples. What happened next? Next we want to update the generator, okay? The generator is very bad now because all of its samples are considered as generated. So the generator is in a bad state. What do you think of the generator happen if you update the generator? The generator here learns something that it produced its samples around one page, okay? The easiest way to update all of these samples all together is by changing some parameters in the neural network. But because the structure of the generator is such that the data is generated in colony, the data are generated near each other, all of them together go to another peak of data samples. Why this happens? Because the training forces the generator to generate samples which are very similar to each other. And when you update it, it wants to seek another peak of the data samples, where in that point, the discriminator assumes those samples to be true data samples, the objective of the generator. So they put all of them in this point. What happened? The generator cannot diversify its samples. it generates samples that are very similar to each other. And now you update the discriminator. What happened? What do you think of what happened next?
To jump to the next.
Yeah, this discriminator completely neglect this peak and assume that these two are true data distribution, and again tolerate the misclassification of these four, for example, points. Again, generator update and go to another mode, and this procedure will be continued. This problem is called mode collapse in GANs. Yes?
Is the generator generating samples similar to each other always true, or true for like just this example?
Yeah, this is what happened in practice. What happened in practice is that when you samples from a GAN which is stuck in mode collapse, you see some samples that are really similar to each other conceptually. Yeah, that's really exactly the problem. Yeah. So yes.
How can we see this mode collapse problem here?
Yeah, these are different samples using different Z. Okay, they are very diverse samples in Z, but the resulting X are very similar conceptually to each other. This is the problem, that it is stuck in a mode. It means that most of its samples are generated in a similar way. And you will see that the diversity of the generated samples in GAN is one of the most challenging problem of GAN. The diversity is not as much as, for example, diffusion models. Diffusion model can generate very diverse range of samples. And the problem conceptually, you can also conceptually understand why this happened. In GAN, you want to generate samples which is similar to your data distributions. It is not important that your generator cover all of the peaks in data. If it can focus on one of the peak of your data, then it can generate samples which is similar to your true data distribution. Because in that point, again, everything is similar to data distribution. It means that assume that the data has some peaks, for example, let's see, sorry for, we have several markers the other day, I don't know where are they. Assume that your data have several peaks. It means that
Generating high markers.
Really?
Yeah.
Thank you. Oh, sorry. Thank you very much. Great. Assume that your true data distribution is something like this. What if your samples are your generated samples are concentrated here? Again, you have something which is similar to data distributions, but it does not cover other modes or other peaks in your true data distributions. Based on the distance metric you design in GAN, this is a great idea. But we know that if we have a optimal discriminator, the discriminator with enough capacity, then you have JST. JST of P data and P theta. And what does it mean? It means that when you approach this JST, it must cover all the peaks, because JST look as both of them, in contrast to likelihood, okay? But because you do not have a high capacity discriminator and you are limited to one neural network, then you have mode collapse problem. And you see here that why the samples are generated similar to each other. Any question? Yes.
So mode collapse here is the generated samples are limited to one part of the distribution of the data.
Yeah.
So I'm just curious, why this does not happen in other models? Like, what is different that is happening here?
Yeah. Assume that, for example, in VAE or other models that we talk about, what do? They are based on KL divergence between P data and P theta. Okay? What does it mean? It means that or equivalently, you want to maximize the expectation of p theta of x over x coming from p data. This is the important part. The samples, when you are sampling, cover, because you are sampling from the true data distributions, you cover this mode, this mode, this mode. If your model does not have high likelihood in this mode, then you have a problem here. You know, assume that I start sampling from the XP data. So definitely I have some samples from here. When I generate that samples, the model understands that it gives low probability to this sample. Why? Because it is 0 here. So it updates its parameters so that it can cover this mode too. And this mode collapse is the problem, the main challenge, one of the main challenging GANs. Okay. Now we want to talk about a larger family of GANs, which is f-GAN, and you will see how the family is extended via f-divergences. Okay. We have seen the original GAN uses the following divergence. The divergence in f-GAN is this divergence, and we want to minimize this divergence, so the optimization is the minimization of this with respect to model parameters. But we have a definition of f-divergences. What is f-divergences? Given two distributions P and Q over random variable x, the f-divergence is defined as this function. Here, if you replace f with log, what do we have? Yeah, we have the...
Shouldn't that be P?
What?
Integral of P effects, not Q effects?
No, there is some changes here, I think. I think this is the correct definition, but I will check it.
Because if you make that log, then it would be the KO divergence only if it's P effects, not Q effects.
Yeah, you have a minus here because of... Yeah. But in f-divergence, this f must have some properties that are important. The first one is that f is from R positive to R. It means that it accepts the samples from R positive. Why it is needed here? Because its input also, this is not a limiting, but you know that the inputs are all from R positive because they are the ratio of PDs. It is lower semi-continuous. This property is to some extent complex to explain here, but assume that it is continuous because all of the functions that I think we deal with are continuous, and continuous is a more general property of lower semi-continuous. So another property is that f1 equals 0. What does it impose? What do you think? It imposes that when this is a divergence, okay? When the distributions assign similar value to an x f1, it means that the argument here is 1, you have 0. It means that when they are equal, you have no loss. Do not add any penalty to your divergence. They are equal. Okay? This provides the property that if two distributions assign a same probability to a sample x, then the loss or the penalty is 0. It is trivial because they are exactly similar in that point. Now we want to use the definition of f-divergence to design f-GAN. Okay, the f-divergences are based on the likelihood. We see that here. That they uses the likelihood of data, but in GAN we do not access to the px, and we access to the p data, but we do not access to p theta. So this definition itself cannot be used for f-GAN. This is the limitation. Okay. Any question? But there is a definition we do not want to deal to understand this convex conjugate in detail, but just as a dual representation of your function. We know that, for example, maybe you are familiar with, for example, a function f and its Fourier transformation. The Fourier transformation is dual, yes?
Why can't we just take the reverse direction of that divergence?
Why?
Because when we studied KL, we saw one direction of the KL divergence we couldn't use, but if we reverse the direction of the KL divergence, we could use it. Is the
the reverse, you mean that the KL between p theta and p data?
Yeah.
Why we cannot use p theta and p data? What was the problem that we do not use that term?
Well, so
There was two reasons.
for the sample,
Yeah, first one is sampling from p theta may be hard.
didn't we come to the conclusion that you could use the KL of QP instead?
In either of the cases, you do not have access. You need in this definition, you need the PDF. Yeah, you need the PDF. But for GAN, you do not have a PDF. You just have a generator of that PDF, but you do not have the PDF itself. The convex conjugate is a dual, is another representation for your function f. Okay? It's just a definition. We just want the definition. We do not want to focus on the property. Okay? It said that every convex lower semi-continuous function f. So our function f in f-divergence follow these two rules. Because it is convex, it is lower semi-continuous, and also it has another property where f1 is equal to 0. Has a convex conjugate form f star, also known as Fechner conjugate, defined as this definition. Supremum is nothing more than maximum. Supremum, the difference is just that the supremum of a set cannot be can be an element which is not an element of that set. Okay, you have a set here. You have a set for for every point t. You should maximize this value over u. Okay, I have a set here. I want to find the maximum of this set. One approach is that, for example, assume that this set is these values, okay? 1.9, 1.99, 1.19, 1.999 until 1. Lots of 9, okay? We know that the maximum of this set is not defined. Why? Because every maximum you give me, I can add a 9 to your maximum, and then this is a new. But the supremum of this set is 2. Okay, this is another definition for maximum. For most of the sets, the definition of supremum and maximum is exactly the same. So just assume that we have the maximization here. Okay. We do not want to start in the definition of supremum, okay? I have a function f of u, actually. F of x, let's see. Now I have a new definition, f star. This is a new function, completely new function. At point t, you want to evaluate this function at point t. What should you do? You should take the supremum. Let's talk about the maximum. The maximum over all possible u in the domain of your function for this term. U times t, pay attention that u is here, t is here, u is your optimization variable, minus f of u. So for each point t, I can find the value of the convex conjugate function. So using the same procedure, I can find f star for all the points. But pay attention that we do not want to use this formulation. This is just the definition. After this point, we just talk about functions and their conjugate, convex conjugate. For example, if f is u log of u, then f star would be exponent of t minus 1. We do not want to. We don't want to know how they can be calculated. Just pay attention that the definition is this one, and as a result of this definition, the convex conjugate for the function u log of u is exponent of t minus 1. Yes.
Dual to another.
Dual.
It means
Yeah, I know. The dual means that the f star is a new representation for f, and every information in f is presented in f star. It means that if you take the convex conjugate of f star, you will again can achieve f. It means that star of a star is again f. Why? Because f star have both property of semi-continuity and also convexity. So you can again calculate the convex conjugate for f star. Convex conjugate of a convex conjugate of f. It is again f. It means that every information in f star is in f.
And what interesting characteristics does the conjugate of a convex function have?
For the f-GAN.
No, just like mathematically.
Mathematically,
The function, what it adds to our information of a function.
Yeah, because the convex conjugate of functions are calculated in some optimization problems, you can use, instead of the function itself, you can use the definition of the convex conjugate, and you have sometimes better convergence speed. Sometimes using f, the optimization cannot be solved, but using f star you can solve the problem. Yeah. If there is a course convex optimization, then in that course they may talk about how f star can be used efficiently in optimization problems. It has a very great and important role in optimization. But here for us, you will see that it changed the problem so that you can calculate the f-divergence using just samples. We have the problem that f-divergence is based on likelihood. This is the problem, and you will see that using the definition of convex conjugate, then you can use just samples to calculate the likelihood, to calculate the divergence, f-divergence. And this is our objective because we do not access to the likelihoods. Okay. So we just have a definition, and we know that they are dual. It means that f star star is equal to f. So this is again the definition of the convex conjugate. Now we want to plug in the definition of convex conjugate to our definition of f-divergence. What was the definition of f-divergence? We can work it here. Okay. The definition of f-divergence was this one. Now I want to replace f. Okay? I know that f, pay attention to this formulation in contrast to this one. Okay, here you have the definition of f star, here I have the definition of f. What happened? Instead of f, I use f star here. Everything is clear? What happened? So I have a new definition for function f as using its convex conjugate. Now I have the formulation of f-divergence, and now I can replace this f using the definition above. So what happened? Instead of f, I exactly replace this definition here. But because the argument I am looking for is p of x over q of x, I replace u with p of x, q of x. Clear? Okay. Now, for each value of x, there is a value t that results in the supremum, okay? For each x, it is this supremum is dependent on x, and we know that in the integral x is changing. So for each value of x, I have a corresponding value t that will reach the supremum, okay? So assume that t bar x is that function. What is the function? For any x, it generates the corresponding t that results in this supremum. So using this t bar, I can omit supremum here. Why? Because it is responsible to generate the corresponding t. Clear? Okay, so I omit the supremum and replace t with t bar of x. And I know that it is a function of x, because if you change x, the supremum will be changed. So I replace both of t values here and here with t bar of x. Now assume two cases. I know that t bar should be should have complete freedom. Why? Because every x has a corresponding t, and this t bar should provide exactly that t. So it cannot be a limited function. For example, a neural network. A neural network has limited freedom. It should be completely free. Any x has a corresponding t, and this function can provide that t. Now I want to limit the capacity of that t. If you access all possible functions, then you select t bar of x, which leads to the above equality. So if I access to the complete set of functions, I find the best one and put it here, and I have the equality. But now I want to limit myself to a family, this calligraphic t. Okay? Then I want to find the best approximation to t bar among the family, this family. It means that instead of having the complete family of the functions, this is the complete family of functions that are from Rd to R. Okay, this is the complete family. If you are capable of selecting any option from this complete set, then you have the equality. But when you limit yourself to a subset of this family, then you have a new function tx. For example, here, assume that the best one is here, then, for example, here, then if you limit yourself to this subset, if you find the best one, which is here, the best one with respect to the true one, the best one in the subset with respect to the true one, then instead of equality, you have a lower bound. Why do we have a lower bound? Because you reduce, because in this function, you find the value of t, which is not the exact value. It is from this subset. So what happened here, instead of t bar, I use t. T is one of the elements in this family. And I also assume, compute the maximum or equivalently supremum for our case, for simplification, over the possible elements of that family. So although I do not find the exact function anymore, but I find the best one, which is here. Exactly to our discussion about the distributions that we are in the set, here exactly have the similar concept. We are looking in a set for the best t. So instead of finding the maximum, instead of finding the f-divergence itself, I find a lower bound to the f-divergence. And pay attention to this formulation. This formulation is very interesting for our case. Now I have this lower bound, and then by multiplying q with this factor, with this term, I have these two integrals. the integral of t of x, px, tx, dx. It means that the expectation of tx with respect to samples coming from p distribution, and also the expectation of f star of tx with respect to samples from the q distributions. So by using the concept of convex conjugate, I found a lower bound to the f divergence. What is the property of this lower bound? This lower bound has a very great property that makes it suitable for GAN generation. In the GAN generation, you just have access to samples. And this lower bound just needs samples. Is it clear why it only needs samples? Because you have an expectation. Expectation can be approximated using Monte Carlo estimation. Monte Carlo estimation just needs samples. It does not need the likelihood. Clear? So, we have a lower bound that can be calculated using just samples. So, thus you have a variational lower bound estimation. Why it is called variational? Because potentially you are optimizing over functions. This is a function. This is the element of a function. So you are optimizing over the. This is the element of a function family. I mean, you are optimizing over functions, so it is a variational optimization. Your estimation is likelihood free. You see here that you do not have p of x inside the expectation. You pay attention that the expectation with respect to the p of x or q of x is valid for us. But expectation of p of x is not acceptable because you do not have p of x. Okay. Likelihood free. Assume that p equals p theta, q equals p theta, then you can minimize the above variational lower bound to train the generator. There is conceptually, maybe you find that if we minimize the lower bound, how it can minimize the value of divergence? What do you think? It is an important point, okay? Assume that the divergence as a function of your p theta is something like this, but you are minimizing a lower bound. You are minimizing this lower bound. For example, this is the lower bound. You are minimizing the lower bound. You are not minimizing the function, the divergence itself. What do you think? Minimizing the lower bound is not equivalent to minimizing the function itself. Maybe this distance is very large distance, and minimizing is not, let's say, interpretable. What do you think? Yes.
What the same thing behind elbow, I think that we hope that minimizing the lower bound would result in.
Yeah. You know, the elbow was a bit different. You know why? In the elbow, for example, if this is the likelihood, and this was your lower bound, you want to maximize there. When you want to maximizing the lower bound is very meaningful because your function cannot be lower than your lower bound. So when you maximize it, it means that the likelihood is also maximized. But here you have minimization. When minimize the lower bound, it is not meaningful. What do you think? Yes.
So you said it's not meaningful because it can just go down, but you're not really improving, right? So is it possible to keep that difference between the lower bound and the actual divergence fixed?
You can decrease the distance. How?
I don't know.
Yeah, it's toward the answer. You know, we have a family, a variational family. Where was it? We have a variational family calligraphic T. if this variational family is large enough, in the case that it is this family, and then you have the great optimization that find the correct value of t of x, okay, then you have the you have the minimum distance between these two. It means that, in other words, the distance between these two is a function of how complex is your family to model T. But by increasing this family, by the size of this family, you can make the distance between these two lower and lower. In the let's say non-limiting case, when you have the complete family, they are exactly the same, and they are bonded together. It means that if you lower down the lower bound, it can easily lower the divergence itself. It is different to variational authentication. Yeah.
My assumption was that the reason why we were choosing that family is that it's like for tractability reasons, you don't want to compute over all functions. But now you're saying the solution is to make the offset family larger. So
yes, I said that it means equivalently, if you have a very low capacity discriminator, assume that, for example, in a GAN, you select a low capacity discriminator. Generally, you do not have a great generative after train because you have a let's say not professional critic. If you have a professional critic, that critic can understand minimum discrepancy between two distributions. But if you limit the capacity of that discriminator or that critic, it means that it can easily be fooled, and it cannot understand the discrepancy between your data and model distributions. The discriminator is very important in GAN and other GANs, for example, f-GANs, for example, by GANs that we will see today.
So is the takeaway here that we have to make it as expressive as possible, which is the same as making the T as large as possible?
Yeah, and also another takeaway is that generally this idea works. So it is not important to make it larger and larger. After having it means that if you have enough capacity in your discriminator, then you are done. You can train the model and you have a great generative model.
So how do you know assuming you're like doing this in practice, then you can't like infinitely go towards more expressivity. You have to sort of bound it.
Yeah. You stop somewhere, and then you train the model, and you see that it works. This is the approach to understand that it is enough or not. Yeah, because it is very complex to understand. For example, for this data set, what is the needed capacity for the discriminator? It is dependent on the generator itself, because if you have a very powerful generator and very low capacity discriminator, generally it fails because the generator can easily fool the discriminator. Okay. Yes.
I don't understand for solving exactly like this question, and for lowering the distance between the actual and the lower bound is to choose from a more accurate family of T.
Yeah. If you make your family larger and larger, the discrepancy between the lower bound and the f-divergence will be decreased.
Okay. So still we have the distance, and lowering that minimizing over the lower bound still does not guarantee.
Yeah, it still does not guarantee, but the important point is that these two are tightly connected to each other. Okay, it means that if you have a discrepancy here, the distance will be fixed by making the lower bounds by minimizing the lower bound. the f-divergence itself will be minimized, yeah, because they are stick together. When you have a complete family, they are the same. When when you have a complete family, they are exactly the same. So minimizing the lower bound, it is exactly to minimize the f-divergence. But when you have the limited family, it means that there is a discrepancy, but the distance is fixed. Assume this type of concept. The distance between them is fixed. So when you lower one of them, the other will be minimized, yeah.
So why this distance is fixed, like why they have connections?
Because of the T. T, the discriminator, assume that you have an optimizer. Everything here is talking about the case that T is the best one, okay? Assume that T is the best one. T is the best discriminator. We cannot call it discriminator. We can connect it to discriminator. T is the best option, okay?
Which T are we talking about?
What?
Which T are we talking about?
No, this T. T in the family, not the optimal.
Calligraphy.
What?
Calligraphy.
Calligraphic is the family.
Okay.
Yeah, this is one of them. And now assume that that's the best option, okay? When it is the best option, it means that conceptually start from complete family. When you start from the complete family, the distance is exactly 0, so you have both of them together. When you start to make your model less complex, then again T tries to model. Let me check. T tries to model. We know that T. Let's say here. T is connected to X. Selection of T is connected to X and also connected to the P of X and Q of X. We know that we do not have access to these two distributions. We have just samples from both of them in the case of data and model distributions. T is responsible to cover all of the complexity in calculating this ratio and then finding the best corresponding T to maximize the supremum. Okay? Now assume that you are in the family that T is limited. If T is limited, the distance between these two is based on the selection of this family. It means that they are stick together and the distance is based on the size of the family. So if you minimize one of them, the other will be minimized accordingly. It is a lower bound, but they are stick together. Why? Because T is optimized in any step. In any step, assume that T is the best one. So it sticks to the true one. We can talk about it after the class. Okay, where are we? Here. So now we want to select the family. What is the family that we can select for calligraphic T so that we can, and also what is the F star? Now, in the case of the f-GAN, we model the family using a neural network. Assume that this is a neural network parameterized by this phi, okay? So by changing the phi, you have a new function. And we have a function that accepts x from Rd and outputs a real number. So can this be considered as our family? Is it enough that the output of our function t is a real number? What is the output of t? what was T intended to do? It wants to mix this supremum, yes? So T must select something from the domain of F star. It is not free to select something from the real numbers. So it must select something from the domain of F star. So we need some matching. Some matching from the real numbers to the domain of F star. So this is the complete family. This is the complete family that accepts a vector in Rd and outputs a value in the domain of F star. If you optimize this family with respect to phi, you select the T of x that we talked about before. But what is F star? F star is calculated for different functions. For example, if you select in the case of KL divergence, it means that the f divergence is intended to implement KL divergence. Okay, f star is equal to u log of u. F is u log of u. F star is exponent of t minus 1. The domain of f star is R, so you have no limitation here, and you do not need this g of f. And g of f, as you see, is identity function because you have R here, and the output of this function is in R, so you have nothing to do with the output. But in the case of GAN, in the case of original GAN, the selected f is this function, and also the corresponding f star is this function you see here. And the domain of f star is the negative real values, so you have some matching. You need some matching, and this function can provide you with that matching. This function accepts input in real values and outputs a number in the negative real values. Okay. But there are lots of samples for f and f star, and you can check them in this reference. And there are different f-GANs based on these options for f. These are just two ones that is near to our discussion, but you can find several of these f functions in the reference mentioned here.
I'm sorry. Yes. What does the column titles mean? KL and GAN?
It means that the divergence is calculating based on KL. It means that the divergence is exactly KL divergence, the f divergence. Here means that the f divergence is something similar to JST, but it can handle that minus log of 4. It is not exactly the JST.
So the one that you calculated in the previous slide is the KL one.
In the previous slide?
Like the divergence here, the D of f.
No, this is the general. This is, we do not limit f. You see, I use f star. We do not limit the f in the discussion. Just here I talk about f. What is f? Yeah. Okay, and you can easily check. You can easily check that if this is the optimization for f-GAN. You want to maximize with respect to phi. Why? Because you want to find the best t of x. So you want to maximize with respect to phi, and you want to minimize with respect to theta because you want to train your model. And the maximization of f can be a new distance metric. Previously, we see that the maximization of the misclassification, the maximization of conditional likelihood was a great option in original GAN. Here we have a extension to the previous part, and this is a new divergence function. This is a new divergence function, and you can use it as your L of theta in generative model. And we see that where are these come from? These are exactly the result of this supremum. we replace the supremum with maximum, and also instead of t of x, we use gf of t phi of x, because these two functions together produce our family, produce our t of x function. We know that this is a matching function that match the output from real to the domain of f star. This is exactly what you have here. There's nothing more. The minus is inside the expectation just. The minus is inside the expectation. And we know that if you select f, you have f star. And you can design a family t phi and you can train your model. So let's focus on the special case of f-GAN, which is the original GAN. What happened here? So for the case of the original GAN, you can see that it is just needed to replace, it is just needed to replace this f and f star inside this formulation. And then you will reach the definition that in GAN, d phi of x is gf of t phi of x, which is equivalent to the this matching one. And you know that 1 over 1 plus exponent is the matching part. Okay, then you can show that the distance of f-divergence will be simplified to our previous divergence in GAN. You replace this d phi, you replace this gf as this d phi here, and you can see that you have the previous formulation. Just use the f star from this column here. Just use this f star. Okay. And what is the architecture for a f-GAN training? You have a z, a latent space, a generator g theta, and generated samples. Also, you have your data samples. Both of them are given to your t of x, and the t of x generate an output in real numbers, and then you match the output of t of x with your with the domain of f star using a g f. This is the complete architecture for a f-GAN. In the case of GAN, you have the discriminator here, and this g of f is inside the loss, classification loss. You want to maximize the probability of y given x. The matching is inside this maximization part, and you will see that how you can. We have seen previously that how you have 1 over 1 plus exponent of p of t of phi of x. Why this is the classification, conditional classification loss. Yes.
The previous slide, where does this log change? This log, yeah.
You know, here g of f, okay? G of f is this function, okay? So I replace g of f with this function here, and you have, to reach this point, you can easily start with the f-GAN.
No, I know, but like g phi equals to g of ft phi x, okay?
Pay attention that gf is not present in the GAN architecture. It comes from the loss function, as I said here.